Thank you very much. Thanks, Carrie. Thanks, Paul, for the invitation, and thank you all for coming. It is a pleasure. So I'm Paulo. Today I'm going to talk a little bit about time series. So I'm Portuguese. I was born there. I grew up there. In 2013, I moved to Brazil. So the weather is a big thing for me. So this is there. So the temperature, I'm here in the Northeast in Salvador. Temperature never drops from the 24, and I like it. So I'm on a sabbatical leave. I'm on a 12-month sabbatical leave. So I'm spending 6.5 months in Monash, at Monash, and then I'm going to Indonesia for almost 6 months as well. And then I'm here. So this is I put this here because that was my first trip over the Pacific, and I learned something on that trip because it was during the night and I could see the sun. I've never experienced that before, and it took me some time to realize why that happened. So I discovered that the planet is not flat, because I can see the sun, which is shining on the north hemisphere. So I was coming here and I could see the sun on my left-hand side, which was the noon sun in the north hemisphere. But it took me quite some time to understand that, because I was looking at Google Maps at that, but I discovered it. So it was slow, but I learned it. So I spent my time doing some teaching, doing some research, supervising students, and I spend some of my time doing service to the scientific community. So I'm a little bit involved with some statistical associations, international and national. So I do also something on co-editing journals. And something that I didn't put here is that I was, 1 month ago, I was selected as the educational ambassador for the American Statistical Association in 2024. So that means that I'm going to Oregon for their meeting, and then I will have 1 year to give some course on that, especially in developing countries. So I think it is, from my point of view, it is important to bring some training to developing countries. That's something that I feel that I should do. So I was asked by Paul and Carrie to say a few words about the ISI. The ISI is the International Statistical Institute. Is in terms of world spread, is the largest statistical association. So it was founded in 1885 in London. It has members from more than 130 members, and they have elect members, which is a kind of prestigious membership, which you have to be recommended by 3 elect members to become one, and they have regular members, and also institutional members. It is also a consultative body for the United Nations. The mission is to lead, support, and promote the understanding, development, and good practice of statistics worldwide by providing core global network of statistics. So this is more or less the main goal of the association. There are 4 main strategic priorities at this moment. The first and the fourth are I think, common in most statistical associations and scientific associations in general, which is membership development and encouraging networking. But the second and the third, I think they are especially important projects. One is related with capacity building to train the world on data and statistics. And the other one is public voice of statistics. I will say a few words about each of those in a moment. The ISI, they have 7 associations under their umbrella. So anything that you do, you will be a good fit for at least one of them. So you have something on survey, something on education. Bernoulli is more on mathematical statistics, business and industry, statistical computing, environmetrics, everything related with environment, and official statistics. And also they have 21 committees. They have one for young statisticians. They have outreach committees in Asia or Far East Asia or South Asia. And for the committee on women in statistics, they have many committees. So myself, I'm mostly involved in this one, in the ISBIS, and this one, the IASC, the statistical computing. So this is the executive committee. Shuming is the current president. Fabrizio will start next year. And there are 4 vice presidents. One of them is Kerry. And there is Denise from Brazil, Oliver from Kenya, and Jessica from the US. Public voice. Public voice, I think, is very important because I'm a statistician. I consider myself a statistician. And I know that we are very bad at marketing what we do. We do a lot of nice things, but we are so bad at explaining people that those things are very nice, and we just don't do it. So I think this is a very important initiative, which is led by Kerry. And the idea is to try to strengthen that a little bit. And the other one that I mentioned before is the ISI Academy, that the aim is to help in providing capacity building. We also have several awards. We have the International Prize in Statistics, which the idea is an award sponsored by the main statistical associations in the world, like the ISI, the Royal Statistical Society from UK, the American Statistical Association from the United States, Institute of Mathematical Statistics, and I think maybe the Bernoulli. And essentially the idea is to give every 2 years some kind of award to the most important, like kind of Nobel in statistics. And the last one, the last one that received was C.R. Rao. He has passed recently, and is one of the founding fathers of a lot of statistical methods. And there are also others. There are awards for young statisticians. There are service awards. So there are awards. The associations themselves, they also give awards. So I think this is a kind of a way of the association to give back to the members, because the members are contributing and they can get some recognition. I list here a lot of, because I'm selling, right? I'm trying to do this that we are very bad at doing. So I'm trying to tell you that it could be interesting to join the ISI. So they are here a lot of benefits of joining. They are in a very small font because there are many benefits. And yes, so if you are interested, you can go at isi/web.org, and then you see all the activities that we are doing there, and all this information. And of course, I told you that I'm involved with IASC and ISBIS. I'm going to talk. I have 2 slides for ISBIS because I'm the current president. So that's my duty to tell you, join us because we are great. So just consider that. So we are International Society for Business and Industrial Statistics. Some of the nice things that we do, we organize webinars and conference and all of that. Our next conference will be next July. Maybe you would like to join. We have a journal, the Applied Stochastic Models in Business and Industry. And at this exact moment, we have a group of young statisticians. So I think some of you could qualify. This is for early career. It is a way of interacting with other people around the world. So for us, a young statistician or an early career statistician will be someone that is studying any level of studies or finished in the last 10 years. So it is quite a broad idea. So at this moment, we have 2 calls. One for members of this YBIS committee for younger and early career statistician, and one for the ISB's newsletter editor. So if any of you is interested in getting involved with this, both of those can be interesting to get involved. Yes, so if you are interested or you want to know more about that, just let me know. And of course, this is the last one about publicity. This is our next conference will be in Yogyakarta in Central Java in Indonesia. It will be in the 11th to 13th of July. And I put here some pictures because, you know, when we go to a conference, it's not just for the scientific, you know. Usually we don't remember what that talk about regression or linear model. We remember about the volcano or the statue or something like that. So although the deadline has finished less than 2 weeks ago, if you are interested in attending, please talk to me that we are still working on the program and we might fit you in, okay? It is a nice place. I was there and it is very nice. So now I think I should talk about something serious, right? So this is what I'm going to talk about. So the idea is time series forecasting. I'm going around a technique called singular spectrum analysis, which is a way of decomposing a time series in several components. And then I have a couple of applications, and then I will have also a couple of slides of other research directions that I work. So forecasting, everyone wants to forecast, right? Everyone wants to know what happens tomorrow. No one will be able to do that, but we keep trying, right? So there are many models for time series and for time series forecasting. And more recently, in the 2000s, some other kind of methodologies, because, you know, we have the statistical models like the ARIMA or the exponential smoothing that all statisticians heard about, but we also have the recurrent neural networks. And those are different kinds of models that can forecast the same kind of data. So the idea of hybrid methodologies, that's what I'm going to focus more, is to try to combine both worlds, the statistical models and the neural network models. And these are hybrid methodologies. Ensemble are also in some similar way, but we are, imagine that I want to forecast something with an ensemble method. I forecast the same time series with different models, and I try to combine like a kind of average or weighted average or something like that. But I will come to that in a moment. So this is not very clear, but I like this this phrase. I don't know if the author is real Niels Bohr. I couldn't find it, but it says that prediction is very difficult, especially when it is about the future, of course. And here in this sketch, the boss is saying that decided to go for some rolling window forecasting. And then one of the funny employees said, okay, so if the problem is that forecasts are worthless, the solution is that I should do more of them. Like a rolling window is when you are doing more forecasts. And then he continues, if sarcasm is a problem of mine, maybe I can solve it by doing some more of them. So yes, the most well-known models for time series. ARIMA, of course, the average, the autoregressive integrate moving average. It has limitations because to fit a model like this, you need data to be stationary, which is a characteristic in which we assume that the mean is constant along the time. So I'm talking today, if you have any question or anything, just interrupt me at any time, okay? So I'm going to focus on a univariate time series. Everything that I'm talking about, or almost everything, can be generalized by multivariate. Univariate is if I have the temperature, the daily temperature in Brisbane. Multivariate is if I have the daily temperature in Brisbane and Melbourne and Sydney. Okay, something like that. So I'm going to focus on a single time series, which is essentially a vector, okay? So the ARIMA, it assumes that the data is stationary. So meaning that the mean is constant and that the variance is constant along the time. And then also the autocovariance is also constant. So, and that is not true in many applications. So we do some transformations to try to make it stationary, but even though it might not be the best model. So that has, of course, advantages and disadvantages. And then you have recurrent neural networks. So you have the basic neural networks like multi-layer perceptron, which usually is used to classification for simple tasks. And when you have data that is time dependent, usually the best is to use recurrent neural networks. For instance, if you have time series, that's a case of data dependent, time dependent data, but also if you have text. When you have text, it depends. So if I say I'm going or going I'm, it is very different. So there is the order matters. So those are the two main fields where we use recurrent neural networks. And of course, there is a big limitation of that it cannot handle both linear and nonlinear patterns. So what I want to say with this slide is that all methods have advantages and disadvantages. In 2003, Zhang proposed an idea of combining these two ideas. So let's bring some strengths from statistical models and let's bring some other strengths from the neural networks. So what he did was, I don't know if I have it here or here, but what he did was to propose some hybrid methods. So what he did was, if he took a univariate time series, he fit a hybrid model, and you see, when you fit a model, there is some noise that is left, right? The noise will be the difference between what the model could capture and what was the original data. So what he did was to fit the Riemann model, and to the residuals of the Riemann model, he fit a neural network. So that's a hybrid model. Essentially, you fit a model, and then to the information that the model could not capture, you fit another model, something like that. So that's what he did, and he called that hybrid model. Sorry, I don't know what happened. Yes. So, and those are hybrid. There is also a class of models which are ensemble. Ensemble is you have like a time series, and you use a model to forecast that time series. You use another model to forecast the same. You use several models, and then in the end, you do some kind of average or weighted average or some kind of combination to get a single forecast. So that's the main difference between ensemble and hybrid. Of course, when you do hybrid forecasting, when you want to obtain the forecast, so what I do is I take my historical data and I forecast what happens tomorrow with Yarima, and then the residual I forecast with a neural network. So I have two forecasts for tomorrow. I will have to sum them because I'm forecasting what is the signal, the one that was mostly captured by the first model, and the noise of the first, and then I sum them to get the final forecast. So what I'm going to tell you a little bit is about singular spectrum analysis, which is used in a way to help in hybrid models. So singular spectrum analysis, it goes back to Broomhead and King in '86, and it is a way, yes, please, yes. Oh, yes. Okay. Thank you.
I don't know much about time series, but I was just wondering, so when you fit the first statistical model, there'll be like an assumption on like the errors of that model. It'll be like, you'll be assuming like IID, like residuals.
No, yeah, good question, thank you. Yeah, so okay. the question is if we have to do some kind of assumption of the residuals of the first model, if they have to be IID or something like that. So the idea here is that the first model cannot capture all the relevant information. Because you see, if the residuals are just IID, like white noise, there is nothing else to capture by the second model. So essentially, it only makes sense to go for a hybrid when the first model does not leave IID residuals. Yes. Yes, the ideal is... Oh, yeah, oh, yes. So the question is that even though we don't assume anything on the residuals in the first model, if we should assume on the second, right? That's what you asked. Yes. So the ideal is that after we fit the two models in sequence, we are left with white noise, like no information. This is the ideal. But it might not have, because you might have a very difficult pattern to capture even with this kind of models. But that will be the ideal, that the final residuals will be just white noise, meaning some time series with no information on it. Yes, thank you. It's because of the...
So if there's no distributional assumption about the first model, then how does it fit? Is this just like a least squares fit or something? Or how are you fitting the first model if you're not assuming anything about the error structure?
It depends on which kind of model you are fitting. So, because you see, you might very well fit an ARIMA model, and you conclude that that is not good enough for your data.
But isn't it? I mean, a Riemann model. That's a statistical model. That assumes you've got these terms, and then you assume you've got Gaussian white noise. So that is, and it's usually fit likelihood-based method or something like that, right?
Yes.
Okay, so it is a statistical model. You're fitting maximum likelihood, and you are assuming the residuals. You're just fitting an additional model to the residuals to make sure the residuals of the residuals is white noise.
Something like that.
So it's basically like fitting an ARIMA model plus some other term.
Yes, because actually you only look at the intermediate residuals as the beginning of the next model. Exactly.
Right, sure. So you could fit you could fit some kind of non-parametric or something like that too.
Anything that works with axis. Yes. Thank you. Yes.
Maybe even making this comment, I'm going to show my age slightly, but there was a lot of work done on neglected nonlinearity back in the 90s, like mid to late 90s, where basically this is exactly what people were doing. They were fitting a linear model and then actually seeing whether there was any extra nonlinearity left over. So we're trying to approximate these things with basic sort of MLPs or something like that, and actually physically testing, like a formal statistical test, to whether there was any neglected nonlinearity, and then kind of thinking about what form it was. I mean, I guess back then there were no big, heavy machine learning methods or anything, so people weren't fitting very complicated models to these things. So, however, then do you know with this kind of newer stuff, are people doing testing at different stages, or is it just throwing the black box at the residuals and sort of seeing what happens?
Yeah, I think mostly what people do is to try different combinations and try to check if in the end the residuals are real white noise or something close to that. I think mostly people are doing that, but maybe there are some works on those as well.
So I just have a question whether my understanding is correct or not. Based on what I've seen and what I've heard is that you use these intermediate residuals and use like another method like k-means clustering to maybe see the behavior. Is it correct that we can, by using this machine learning and neural networks, we can maybe decide on the characteristics of the data points that we have initially that we can't explain by just a statistical or ARIMA model? For example, if we get some sort of extra information by clustering them, we could go to our initial data points and saying that that's some extra information we can get that otherwise would not have been observed just by using the ARIMA or any other statistical methods. Does it make sense what I'm saying? Or
maybe because you see, if you think about clustering, I guess that you will think about the multivariate time series.
Yes.
Right.
Yeah.
So probably what you are doing is to do some fitting in similar clusters. The simplest case is really to fit the model and then to fit something else on the residuals of that model. Of course, you probably can do something on these similar clusters. What I'm going to talk about, singular spectrum analysis, they create subseries. They separate the signal of a series in similar ones. So maybe in that case, it would make sense to do some clustering to try to see what are the patterns that are captured by one or by the other.
Yeah, I see.
Maybe in that case. Thanks.
Thank you.
Anything else?
Thanks, Paulo. I'm just going to follow up because I think one of the questions that Connor asked that I'm not quite sure that was answered was at the moment you fit a statistical model and then a machine learning model, okay, or a neural network. And I think what Connor was asking is why not the other way around? Why not a neural network and then a statistical model? Like, why do you start with the statistical model?
Yes.
Is that right, Connor? Did I get that right?
It could be the other way around. Yes. I guess that it doesn't have to be like that, the order, but I guess that people do that because maybe the neural networks are more general.
It would be cheaper to fit the ARIMA model first,
Yes.
and then if you don't need anything else, you stop.
Yes.
Rather than fitting the expensive model, doing the machine learning first, jumping to conclusions like the silly bunny, and assuming you need the machine learning model first. So it's cheaper just to do the ARIMA model.
Yeah, because you can even, you don't have to do, when you think about the general concept of these hybrid models, it doesn't have to be a statistical model and a machine learning model. It can be two neural networks or two statistical models. So the general concept, it might not work as well, but the general concept, it can include any kind of combination.
As long as they're orthogonal, it shouldn't matter the order.
Yes.
So yeah. What? So yeah. Yes.
Yeah, shall we keep going?
Oh, no, I was just kind of coming back to that point. I think the logic, I mean, I haven't read, well, talking about that older kind of literature, I mean, what the concept was that a linear model should do a lot, and I guess then the question is there anything left over? So, I mean, if you start with a machine learning model, well, it should be capturing the linear stuff, but it might not be actually doing anything else. So I guess you kind of, in some sense, are not necessarily thinking about cost, but just the actual logic of what the model should or shouldn't capture. You start with the simpler one. If there's nothing else left, then sure you need, if there is something left, yeah, sure you need to use something better, more complicated.
And if you do this statistical model first, you can do the inference.
Yeah.
Thank you very much. Thank you. So what I'm going to talk now is about this singular spectrum analysis. So it is a non-parametric. It is a kind of combination about those things that we know about time series, some multivariate statistics, and some matrix algebra. So we assume that at univariate time series, we also have the multivariate singular spectrum analysis, that a time series can be represented as the sum of individual components. I will tell you how to obtain that. So this is more or less how it works. This Goldin, Dean and colleagues in 2001, this is a full book on this technique. So first we do decomposition and then we do reconstruction. So let's imagine that I have a univariate time series, like a vector. The first thing that we have to do is to create a matrix out of that vector. We call this trajectory matrix, and essentially we have to select a window length. I will come in a moment to that. We choose a L window length, and what we do is that the first L observations will be our first column of the matrix. From the second to the L+1 will be the second column. and so on, until the time, so essentially we have the time series, we have this moving window, one by one, and when it reached the end, that will be the last column. Okay, so this is the first step, to go from a vector or a time series to a matrix. The second one is the singular value decomposition. I don't know if all of you remember about that, so I put a slide to give a summary of that. So imagine that we have a matrix X with rank R. So we can decompose singular value decomposition, decompose that matrix in the product of three matrices. The D is a diagonal matrix, which has the singular values on the diagonal. The U and V, they are orthogonal matrices, and they have the left and right singular vectors, okay? So imagine that I want to reduce, so this is what is used, for instance, in principal component analysis. We want to reduce the dimension of the data. It's not exactly the size, it's the dimension. So imagine that I have an n times p matrix, like the X, and I want to reduce the rank to K. So I'm not reducing the size, I'm reducing the rank. So what I do is if I want to go from R, which is greater than K, to K, I take the first K columns of U, I multiply it by the P by P first part of this diagonal matrix. So this is the diagonal matrix, everything here is 0, it is only in the diagonal we have something, times the K first rows of the B-transpose. And of course, if we make that product of what is in black, we still get the n times P, but is a reduced rank matrix. Okay, so this is the idea of the singular value decomposition, and this is what is obtained when we minimize, for instance, this Frobenius norm. So we are minimizing the distance between the original matrix and this low rank matrix, okay, in some kind of distance. Why am I talking about that? Because the first step is to create a trajectory matrix, the second is to do singular value decomposition on that. Okay, so that's what we do here. And then this is my Y, the trajectory matrix. I'm decomposing it in the sum of rank 1 matrices. So essentially, what I'm summing here, so this is my left singular vector, the right singular vector, and the singular value. Okay, so essentially what I'm doing is to say, okay, the original matrix is this column times this number times this row. That's a matrix of rank 1. That's the first. Then we go for the second column, position 2, 2, second row is the second matrix. And we continue until the end, essentially. Okay, so what we are doing is to say, okay, my original matrix, this trajectory matrix, can be written as the sum of a lot of matrices, all of them with rank 1, okay? That's the second step. The third step is, you see, now we have a lot of matrices, but the idea of this singular spectrum analysis is that we are going to make a kind of division between what is signal and what is noise. So signal means that I have a component that is a kind of trend or seasonal or something like that. Noise is just noise. So that's the first step. The third step, we have to find a set of indexes, I, that the components that are in that set of indexes, they will be associated with signal. Everything else will be just some kind of noise. Okay, so that's the third step. We are separating in two parts. The components for the signal, which have a meaningful interpretation, and the components for the noise. The last step, you see, we start with a vector. Now we have a lot of matrices. So we have to go back to the time series. So that's what we do here. So this is a formalization of something called diagonal averaging, but in practice, what this does is something like this. So imagine that I have a matrix, and I want to map that matrix in some kind of vector. So what I do is that my position 1, 1 will be the first position of the vector. This average of those two will be the second position. The average of those three will be third position, and then we continue until here. So it's a kind of averaging in this, I don't know what to call these diagonals, anti-diagonal, I don't know. Yes, so the diagonals in this direction. So that's diagonal averaging. So what do we get? So remember, we start with a univariate time series, we create a matrix, we decompose that matrix with singular value decomposition, we decide, okay, these many are going for signal, these are going for noise, and then we are combining back together, so we are saying that the original matrix here, the original time series, now can be written as a time series associated with signal components plus a time series associated with noise components. So it's a kind of decomposition technique for time series. So why is that important? Because the underlying idea of this technique is that, okay, if we only use the signal for forecasting, we get better results because we are getting rid of the noise. So there are two decisions that we need to make. One is the window length, like for creating trajectory matrix. Usually this is selected to be near to the middle of the time series and proportional to the number of observations per period. For instance, if you have monthly observations, you assume it proportional to 12. Imagine that I have 100 monthly observations. Probably I'm going to choose 48 because it will be multiple of 12 and it will be close to the 50. It should be, the L should be between L divided by, between 2 and half. So the window length should be between 2 and the middle of the series, n divided by 2. So, but the ideal is to stay closer to the middle. That's one thing that we have to decide. There is no mathematical formulation for that, the same as in some other non-parametric ideas. The other one is the number of components, the one that I mentioned in this slide. So how many components are going to be the noise, or how many are going to be the signal? And this is the same problem as we have in principal component analysis. When you use principal component analysis, we have to decide how many components are we going to get. So there are many ideas and suggestions to choose that number, but none of them has a kind of universal result. So in this case, what we do is we use some kind of correlations. So what we want, imagine we have all of these components that we create from the trajectory matrix. So then we do the correlations between all the pairs, and what we want, we are separating. The idea here is to separate signal from noise. So what I want is that the components in the signal to be homogeneous, to have high correlation between themselves. The components of the noise, they might also have high correlation between themselves. But when I have components from the signal and from the noise, I want that correlation to be low because I want to separate two groups. So high correlation in one, high correlation in the other, but low in between, right? And for that, we do this kind of double correlations. And this gives us some kind of plot like this. So these are the indexes for the components. I have here 25, for instance. So this is a correlation matrix. I have here the black, it is 1, the white, it is 0. And then, of course, in the diagonal, I have 1. It is the correlation of the component between the component and itself. And I have to look at this and try to imagine what is a good place to split. So if I look at here, I can say, well, maybe I can split here or I can split here. Because, of course, I should not split here. Because if I split here, it means that there is a big correlation between the component of one side and the other. So I should look at this and try to decide where to split. And it is, of course, a subjective task. Then, after doing that, we can do forecasting. And the forecasting, there are several techniques to do forecasting in this methodology. One of them is to use a linear recurrent formula. So essentially, I'm saying that what happens today is a linear combination of what happened in the last L days. Okay, so I'm essentially doing a linear combination. So this is the observation in day t minus 1, etc. So this is our past observations. We have to estimate these a's, and they are estimating with this more or less complex equation, which essentially, remember in the singular value decomposition that I said that u was the left singular vectors, so that's that u there. So what I have here, this is that matrix except the last row, and these are the observations in the row of that u matrix. So there are some reasons for that, and in that book of Colli and Dina, they have a proper explanation for that. So those are the coefficients for that equation here that will help us in doing the forecasting. And of course, if we want to do forecasts for tomorrow, I use error here for forecast and tilde for approximation. So I'm using only the signal. Remember that we're splitting between the signal part and the noise part. So I'm only forecasting with the signal because I'm assuming that the noise is not so important. And of course, if I'm forecasting for 2 days ahead, I can already use the forecast for tomorrow and then fit the values for the other observations. Okay? Any thoughts here or comments or questions? So the idea here essentially is to take the time series, which can be univariate or multivariate, in this case univariate, and I'm creating two groups, a group of signal and a group of noise. I can also create a group of seasonal components and a group of noise and a group of trend components. Okay, so essentially I'm decomposing. Like for those of you that work with time series, there is the STL decomposition or some other decompositions. That's a different way of decompose. But we go a little bit in more detail because we are decomposing in components, which then we group. Okay? Why am I talking about that? Because then what we tried to do here was to use that information to try to help in forecasting. So what we did was, so first we did this singular spectrum analysis decomposition. We have two time series. So the idea is that we have the original univariate time series, then we decompose into one for the signal, one for the noise. And then what we did was we forecast the signal just with that recurrent linear formula, like that linear combination. And then the noise, because you see, there is no way that what is left here is noise. If you come back here, there is no way that this is white noise. Because you see, we are looking at this. We are looking at these spots and say, okay, this is signal, this is noise. Or maybe this is signal and this is noise. So there is no way that what is left is pure white noise. So I'm calling noise as a general concept, not white noise. So what we thought is that, okay, so that's not white noise. So let's try to do something with that. So that's what we did. We put we just did we forecast signal. And then the residuals that came from the singular spectrum analysis, we put a neural network there. Yes?
So, when you're talking about the residuals, once you take the signal out, but that's different to here, because here you're talking about the residuals from a linear model, aren't you?
So before, when I was talking about hybrid, I was just saying, okay, I'm fitting this, and to residuals of that, I'm fitting that.
Yes.
Right? Here, I'm doing differently. What I'm doing is that I'm using this singular spectrum analysis to split in two parts.
Oh, right, okay.
Something that is I call signal, and something that I call residual. If I add those up, I get the original signal.
So this is not a...
It's not sequential.
Sequential, yeah,
yes,
okay,
exactly.
yeah.
So I'm splitting first, and then I work on those.
Yeah, okay. All right.
Each of them. Okay. So that's what we do here, and then of course in the end we get a forecast for the signal, we get a forecast for the noise, and then we combine them. Okay, and we did in this paper. This is a paper where we use data on electricity load data from Java and Bali. And what we did was to do this with the neural networks, but also use some concept of fuzzy time series. So we consider both in the same way, and these are the results that we obtained. I don't want you to look at all those numbers. I'm just telling, so these are some kind of standard techniques for time series, and then these are the combinations. So I have here the ones that, this is the SSA with a neural network. So this was a multi-layer perceptron, it was not a recurrent neural network. And these are with some techniques based on fuzzy time series. And this is just when I do the signal from the SSA. So I just use a recurrent linear formula. So I have here the root mean squared error, the mean absolute percentage error, the training and the testing for both of them. If you look for the lowest numbers, they are here for the SSA plus the neural network, and this was not even a recurrent neural network. And you see that if I compare with this number here, this is when we just discard the residuals using SSA, using singular spectrum analysis. So there is a huge improvement here. And you see that it also improves with the standard models, like some of those that are mostly used, like the exponential smoothing, the ARIMA, and so on. So we were quite happy with this. I also have here another application. In this one, we already use recurrent neural networks. This is about PM10, one of the ways of measuring pollution. So this is data from Lima, in the capital of Peru. The data is something like this. You see, there is no statistical model that can capture this. So there are a lot of peaks and everything. So it is very difficult that we capture that easily. These are just temperature, relative humidity, and wind speed. We didn't use those in these results. So that's what we tried to do. We tried to do some kind of combinations. So we forecast, these are pollution. So we try to forecast what happens so this is hourly data. We try to forecast what happens in 1 hour. These are the results. What happens in 6 hours, in 12, and those 24 that I'm not showing here. So what we try to do is to do this kind of combination between singular spectrum analysis and neural networks. So MLP represents multi-layer perceptron. LSTM is probably the most famous recurrent neural network. It's long short-term memory. And SSA is the singular spectrum analysis. When I say original, it means the original data set, like the PM10 as it was observed and of course cleaned, and I think we had to do some imputation on the data and so on. And when I have signal, it means that it's the signal that we got from the singular spectrum analysis. And when I have the noise, is the noise that I got from the singular spectrum analysis. So every time that I'm talking about noise is not white noise, okay? It's what the SSA gave me as noise. So what we saw here is that if you look at, so I have here the root mean squared error, the mean absolute error, and the mean absolute percentage error. And if you look at those, I put here in bold font and also in these rectangles, generally the lowest values, which means that is when we use the singular spectrum analysis for the signal, like that recurrent linear formula, and then especially if you see the LSTM is a little bit better in general. So, and we use the recurrent neural network. So the multi-layer perceptron, of course, is not well fit for time-dependent data. So the LSTM performed a little bit better than that. So that's what we got here. I also try with some students some other things. Here we were comparing the simple recurrent neural network, the LSTM, and the Getter, the recurrent unit, is a kind of LSTM, but it is faster. It is a little bit simpler and it runs fast. So we got some application to, so these are more in the direction of financial data. In this case, we were looking for, because everything that I said here is about point forecast, we also try to look on interval forecasts. So we try to do some kind of bootstrap to try to get also forecasting intervals here. Here we also have some kind of combinations. So we are, is the question that you asked before, that someone asked before. So we are comparing what happens, like it was a kind of simulation study, like what happens if we do ARIM and then exponential smoothing, or if we do SSA and then LSTM in both directions, or the GRU or some. So we're essentially trying to study some combinations to see which can be better in depending on the structure of the data. And here we also try to do something for the multivariate. We didn't finish this yet, but our idea is to try to get the multivariate time series model in the hybrid way. Some comments so far? Yes.
So I'm just wondering, maybe this is like clarification for myself. So like if you're doing like standard hybrid modeling, you might fit like a linear model and then like a non-linear model to the residuals, or like some choice of that. And is the idea behind like the SSA that like you really make sure that you're only trying to fit the linear trend and that all of the non-linearities are in the error, and so then like when you fit the SSA, you're like learning the true linear trend in the presence of non-linearities? Is that the idea? Or?
Yes. So if I understood correctly, and please correct me if I didn't, is when we do the singular spectrum analysis, is if we are trying to guarantee that the linear part goes to one side and the non-linear part goes to the other. That is not exactly, because if you have, because what SSA does is, you see, it's like principal component analysis. The most important information is captured by the first component, the second most orthogonal goes to the second, and so on. So if you have a nonlinear trend that is very important, it will go already to the signal. So we don't have a way of doing that. One possibility can be to try to group those components that are more nonlinear and try to forecast them by themselves with a neural network or with a specific model. That can be done. But there is no way of guarantee that there is linearity and nonlinearity in this, except if you are looking at them and try to pick yourself.
So on that slide of SSA where you show how like the linear decomposition thing.
Let me try.
Yeah, the second.
You mean in the method still?
Yeah, in the method, yeah. So then the linear
Here.
decomposition, it could also have the residuals in it, right? You have only included the previous.
Sorry, can you?
Could also have like the residuals of the model in this, right? This is.
Yes.
Yeah.
So this is actually, so this is not a model. This is just saying, okay, I'm assuming, of course, there is a residual. This is just the residual that you get there is the one that goes to the second group. So you have the signal components and the noise components.
Yeah.
What you get there as the residual, it goes to the second group.
Okay.
Right?
Yeah.
Because of course, you can say, okay, I assume that what happened today is a linear combination of what happened in the last 20 days.
Yeah.
But probably there is something left. It is not possible that it is 100% fit. So whatever is left, it goes to the residual.
Okay.
Is that what you were asking?
Yeah, yeah. I'm like, so where does the ARIMA part come in? Like, where do you make like the model when you say the model is an ARIMA model?
Ah, yes. So in this case, what I present here
Yeah.
was, so when I talked about ARIMA was to some kind of motivation of how
Okay.
this can be used.
Okay.
So for instance, if I decompose a time series in signal and noise, I can very well say, okay, I'm going to fit ARIMA to the signal.
Okay.
In this case, I didn't, but I could do that. I could fit the ARIMA, not to the noise because it would not be good probably, but I could use it there, but I didn't use it myself in these two applications.
Okay.
Thank you. So I have here a couple of concluding, oh yes, sorry.
Sorry, it's a really like qualitative question. It's actually on this slide. I was just wondering, like,
This one.
yeah. Like, are you concerned when the test is like lower than the train?
Yes, this is a very good point. Yes. So the question is, because you see in some places here, the test is a little bit lower than the training, which is usually doesn't make sense. So in fact, that I'm not fully sure if that is a good thing to happen, probably not. We didn't redo, because I did present this a couple of, maybe a couple of months ago, and someone raised that. We didn't pay attention to that, and we didn't redo that yet. We should do and see what was the problem. Because it is indeed a little bit weird that we get better results here than there. So that it might be some small adaptation, but we should check that, and we didn't. Yes.
Maybe they're not.
Probably not, but still you see that they are a little bit lower. I don't know, because it might also have to do with the, because you see, it might have to do with the time series. Maybe in the end of the time series, the pattern was easier than during the training, because the training, it might have some peak or something like that. So it might be due to that as well. But we didn't go into detail. Yes. Thanks. So I have here just a couple of concluding remarks and then a couple of extra slides. So what I want to tell you is that if you are forecasting, consider not just using a single model, using a second model might help. Of course, if you fit a single model and you get white noise as residuals, that's fine, it should be okay. But if you don't, there are ways of taking advantage of whatever information is left there. So that's more or less what I had here. And recurrent neural networks are a good way of help with that. Based on I have a couple of talks in the morning, so I had a couple of slides here. So this is the lab that I'm leading. I have here 7 directions, and these are they are my colleagues and former students that are leading that. So I have something on deep learning and AI. Nigel is a former master student, and he did a very nice work on, he works at Petrobras. I don't know if you know Petrobras. It's a big oil company in Brazil. So he works there, and his job is to find oil. So that's his job, more or less, of course. So what he does, he gets this data. So they have data from like if you slice the ground, they put some kind of sensors. I don't exactly know how it works, but you get slices of what is down there. And those slices have a kind of strange of patterns. And he and some colleagues are looking image by image. So they slice in this way, many slices, and they slice that way. He's trying to see which kind of rocks are similar. He's geophysicist, maybe. So he's trying to see where are those changes in rocks that can hold oil, because the oil goes up, if I understood correctly. So there are some rocks that hold it. So, and essentially what he did in his master was to develop a convolutional neural network to try to take those images and to try to classify them. Like instead of having one person several days saying what is what and what should be grouped, he could do some nice work with some neural networks. Then we also do something on statistical genetics. For instance, I did my PhD on that area, on multivariate statistics and statistical genetics. I have a couple of slides here. We also do some spatial temporal modeling. So this is the map of Brazil. And in Brazil, there are 6 biomes. Like biomes are like a kind of similar kind of environment and vegetation and so on. So you have the Amazonian in the south. You know, in Brazil it snows. Many people are not aware of that. So in the south of Brazil it can snow. So that's the Pampa. And then when it is on the coast, this green is Atlantic kind of thing for the Atlantic Ocean and so on. And the dots, so this is a study where we try to model the number of fire spots in Brazil. So those are January to December. Each dot is a fire spot. A fire spot is coming from a satellite image and is a kind of set of pixels. So these are the locations of the fire spots in Brazil in January 2021. And this is February and March, and you see that if you go to September, October, maybe August, you have a lot of dark dots here, so that's not good for Brazil. So, and basically we are doing some kind of spatial temporal modeling on this. So this is count data, which is also challenging. So that's what we are doing with a couple of colleagues. And then, of course, if I think of this data, you see, I have the number of fire spots. You know, Brazil, besides the six biomes, the small administrative region is municipality. They have 5,570 municipalities. So what we thought was, okay, so we have the time series of the number of fire spots for each municipality, then we have for each biome, and then we have the total. So this is a hierarchical structure. So that's what I'm doing with a couple of students, is to try to look at this hierarchical structure. So this is the total number of fire spots, which can be per day or per month. And these are, the level 1 will be the 6 biomes, and these the municipalities in each biome. Okay, so this is also something that we are doing on that direction, on terms of hierarchical time series forecasting. And sports analytics, there is a big thing in sports here. So I have a student that when I interviewed him for a grant, it was something on time series forecasting. I realized that he loves basketball and NBA. So I told to myself, this guy has to work with basketball and NBA because that will be much better for him. And I don't think I should force someone to do something that they are not so passionate about. So we published a couple of papers. And we were using some supervised and supervising techniques, also some self-organized maps. So we're trying to do some analysis of the historical data. In one of the papers, we try to define based on the data along the time system, because the NBA, they collect a lot of very nice data. So about all the statistics per player, per match, everything. So we could define 3 eras, because there were changes in the way, like the distance between, for the 3 points, I think it changed at some point. So we were trying to see in which way they could create a different, a major change in terms of behavior of the players. Yes, and that's what everything about sports. This is just to remind you that we have this conference in Indonesia. It is a very nice place. So if you think about that, tell me. Sometimes I finish with a phrase. I like this one very much. This is John Tukey. He said at some point that the best thing about being a statistician is that you get to play in everyone's backyard, and I like that very much. Not just the phrase, but also doing that myself. So these are some of the references that I use here. So this is the one of this first hybrid method in neurocomputing. These 2 are relate with this electricity load forecasting. These two are related with this PM10 analysis, visualization, and forecasting, and this has to do with hybrid and ensemble methods. So these are my contacts, my email, my website, my lab, and thank you very much for your attention and time.